Number 7, we're going to go ahead and completely analyze a polynomial function that's in factored form. Our end behavior model, we would look at the y equals, we would look at the degree of the polynomial. The degree is 3 plus 2 plus 2, that's 7, and there's a minus sign there. So negative x to the 7th would be an end behavior model for this particular function. So any we know that goes down from left to right because the degree is odd and the a is negative. The a is the number in front here. It's the coefficient, the leading coefficient. If you were to multiply all these terms out and write this polynomial in standard form, we would see that negative x to the 7th would be the very first term. And then you'd have plus a bunch of other stuff. But therefore, y equals negative x to the 7th is the end behavior model. The graph of this function will go down from left to right. And let's take a look at the rest of this. So x-intercepts, we notice that if x is a factor, so we have three factors, x, x plus 3, and x minus 2. If x is a factor, that means that 0 is an x-intercept. So 0 is an x-intercept. The multiplicity of that corresponding factor is a 3. That means that the graph of the function crosses the x-axis at 0. Likewise, whatever causes this factor to be equal to 0, this factor being x plus 3, which is negative 3, so negative 3 plus 3 is 0. So negative 3 causes that factor to be 0. X plus 3 is a factor. Negative 3 then would be an x-intercept or a 0. Multiplicity is 2, so the graph of the function touches the x-axis at x equals negative 3. Likewise, 2 would cause this factor to equal 0. Therefore, 2 is an x-intercept. Multiplicity is 2, so the graph of the function touches the x-axis there. If x equals 0, we would see this first factor is 0, and that would cause the entire function to have a value of 0. Therefore, the y-intercept is 0, 0. Now, the maxima, we're going to go ahead and draw the graph first before we get into this stuff here, although we know that the domain of a function, polynomial function, is all real numbers, as well as the range of any odd degree polynomial is all real numbers. So we know that. And let's go ahead and plot the x-intercepts here. We have 0, we have negative 3, and we have 2. Again, we know that the graph comes down from left to right. And then, so therefore, we would start high. We have to start in the top left, and we're going to finish in the bottom right. So if we start in the top left, and we approach this first x-intercept of negative 3, we already talked about that the graph of the function is going to touch the x-axis at negative 3. And then it's going to cross the x-axis at 0, but it's going to cross with a squiggly. So the multiplicity is 3, and so we're going to come up, we're going to come down with a squiggly down through 0, and then at 2 we see again it's just going to touch the x-axis at 2, and then the actual graph of the function resembles our end behavior model, so we're good. And finding a maxima, we have let's consider this point here to be negative 1, I don't know, 2, and then this point here be 1, negative 2. So we'll just give these points. Again, we have to estimate some of the values. We're going to just estimate negative 1, 2 for the coordinates of this high point here. That'll give us some easy numbers to work with. So we have a maxima at negative 1, 2. We have a minimum. We also have a maximum here at 2, 0. We have a minimum at 1, negative 2. And it doesn't necessarily say we have to classify these, but we don't have any absolutes. We have local max, local min, and local min here at negative 3, 0 as well. Let's not forget that one. And then now we have to just figure out on what intervals this function is increasing on. Well, it's increasing from left to right when the y values are getting bigger. So from negative 3 to negative 1. and then from 1 to 2, and that's it. Decreasing from negative infinity all the way to negative 3, and then from negative 1 all the way down to 1, and then one last one from 2 to infinity. And that is a complete analysis of that function.